All right, so we're ready to continue on in our guided notes, and we are going to start here on page 16. And this next section that we're going to be looking at is finding the resultant of non-parallel forces. And this is going to start on page 72. It's this section right here, and the first example is going to be down here on page 72 in that PDF of that chapter that I made available to you guys. And as you know, the section just before this that we had completed the last time we were together was a resultant of parallel force systems. So all this means is we now have forces that are going at different angles, and we want to find the resultant for it. Notice that these are not concurrent forces, so they don't all share the same point like we had in module 3. We now are going to have those distances. So we're going to continue to exercise our 3 equations, some of the forces in the X, some of the forces in the Y, and then summing moments. And those are going to help us to find not only the resultant magnitude, but also, and its direction, but then also where it would be placed to have the same net effect on the body. So here it says the resultant of non-parallel force systems is found essentially the same way as the parallel, but now we need to resolve the X and Y components of what will be our resultant. So there's a little bit of an extra step or two here, but we're going to see similarities to things that we've already done before. There are now going to be a resultant X and a Y, and that'll be used to determine the resultants. So I have a question there. It's not really anything to answer, but sounds familiar because we've done that before. So there is a process that we're going to take to kind of go through and find these resultants of non-parallel forces. So we've got an extra step or two, like I said, to parallel forces. So first of all, we're going to be drawing our free body diagram and our convention. Every problem needs a convention on it, okay? So you don't do a convention for a whole chapter, you do a convention for each problem. And we're going to continue to use, I'm going to call it the new convention that includes not only the forces positive, but also the direction of the moment. Then you're going to notice that we're going to break any forces that are not on the X and Y axis into their components. So it says here if it's needed. So we might find that some forces are vertical and horizontal, but others that aren't, then we are going to have to find those X and Y components. Then we're going to determine the resultant component and the resultant. So we're going to sum our forces in the X, and that's going to give us our resultant X component. We're going to sum our forces in the Y, and that's going to give us our resultant Y component. So again, sounds familiar. And we're going to use those two, which are going to be the legs, if you would, of our right triangle to find the resultant. Then we're going to determine the moment generated by those original individual forces about a point on the body. So this again is another step that we did previously when we found resultants of parallel force systems. And then we're going to find the X bar or the Y bar. Now that's going to be the distance from our point that we're summing around to where the resultant is located. And it's going to just kind of depend on the line that we are going to be determining the position on. And that'll make more sense when we do some problems here. And then we are always going to draw a final diagram to show the resultant and the X bar or the Y bar in relationship to the point that you summed your moments around in step number 4. So this last step lets me know that the answers that you've gotten, that you understand what they mean. Okay, so that gives me a picture, a graphical of that. Okay. So now what we're going to do is to practice this process, we're going to do example 4.5, and this is found starting on page 72 and going to page 73. So let's take a peek at that problem. So on page 72 here, right at the bottom, example 4.5 starts. Now, what they want us to do is they want us to determine the resultant of the force system shown in the figure they're referring to here. That figure is found on the very next page. So if I turn the page here, the figure that we are going to be looking at is right up here at the top. Scooch this up like this, up at the top of the page. All right. This is, if you would, our starting illustration. Okay. We want to find the one force, the resultant, that would replace all 3 of those forces and have the same net effect on the body. Okay. So this is what we're going to be starting with. Now it wants us in the problem statement It wants us to locate that resultant with respect to point A. So if we look back at that illustration, point A is in that bottom left-hand corner of the box that we have here, with the other corners having the forces. So we're going to be, as you can imagine, summing our moments around here, okay? And then we're going to be locating our resultant with respect to that point, okay? Now, kind of looking ahead, you're going to notice that I'm going to go down to this final illustration down here. This is where we're headed, okay? So this is what we want to find. We want to find the one force, the resultant, its magnitude, okay? Should end up to be 37 kips. Its direction as identified by the arrowhead and the angle that we see here, and then the distance away from A. So since this is a horizontal distance, we're going to call that X bar, okay? So, and then this would be your, if you would, your final illustration, okay? But we've got to do all the work to get there and make sure that we get the same answer. Okay, so I'm going to start with just kind of looking at our illustration here. So number one, we are going to be drawing our free body diagram and adding our convention to the start of our problem. All right. Yeah, as you can see here, we've got three forces, one on each of the corners that are going around, and each one of those forces is at an angle other than vertical or horizontal. So we will have to find the components X and Y for each one of these forces. Each one of the forces has a magnitude, and you'll notice that they're called out as F1, F2, and F3, and they're giving us the angles. So that's going to be the work that we have to do first, and then we're going to place them around the outside of that box, if you would, and then we're going to proceed to doing the other steps. So step number one is going to be exactly that. We are going to draw our free body diagram, and step number one on the bottom of page 16 here, okay, this is where we're going to be working. Scooch this up a little bit. Okay. All right. And what I want you to do in this space that's provided, draw your free body diagram right now and add your convention, okay, and add your convention. I need to get my straight edge right here. Uh-oh. Now, again, always making sure that as you are, putting your work in place here, we're going to add our convention to the upper right-hand corner of our work, and then making our free body diagram as large as possible. Okay, and then identifying points, distances, and forces as appropriate from our illustration. Okay, so we know that point A is down here. Okay, and I'll kind of refer back and forth to our figure. So notice that we have point D, C, and B. Okay. I think I'm going to put them on the inside, actually. That way they won't interfere with forces that are going to be on the outside. Then at B, it looks like we have F1, which is 12 kips at a 60-degree angle from horizontal. So I'm going to draw that going up and to the left. This is going to be F1 is equal to 12 kips. And this is why I have an eraser. Okay. So this is going to be F1 is equal to 12 kips. Put on this side. And then I am going to have a Y component and an X component. Making sure that we're showing our X pointing to the left and our Y pointing up. So this is going to be F1Y. This is going to be F1X. And this angle here is 60 degrees. So that's my F1. Like it. Try again. It's up a little higher. Trying to be a little heavier so it's easier to see. Then we have our force at C. Our force at C is at 45 degrees. This is F2, and it's 20 kips going up and to the right. So 45 degrees. Okay. Since F2 is equal to 20 kips. And we're also going to have an X and a Y here as well. X is going to point to the right, and the Y is going to go up. This is 45 degrees, and this is going to be F2X, and this is going to be F2Y. And then lastly at D, okay, we have 25 kips going down and to the right, and it's 15 degrees from horizontal, and that's being referred to as F3. So I'm going to draw a little horizontal line there. This is going to be 25 kips. And then we're going to have an X and a Y. The X is going to go to the right, and the Y is going to go down. So this is going to be F3Y, F3X. And this is 15 degrees. So this is our free body diagram and convention. Okay, make sure you have that on there. Remember, if you don't have a good free body diagram with all of the dimensions and the called out, in this case, the components and every one of the vectors with arrowheads, then you get points off. Oh, there's one other thing that I'm missing here. I need to add my distances for the 10 feet and the 8 feet. So I'm gonna just 8 feet, 10 feet. So we want to add distances as well. Okay, so now that I have all of my items in place, then what I'm ready to do is turn the page, break those forces into their X and Y components, and show the work here for what the magnitudes for each will be. Okay, so that is going to be our next step. So go ahead. I'm not gonna dictate, and go through each one of these, but I'll be calculating these along the side. I'm going to do my X's here, my Y's here. I'm going to start with F1 and so on. So using our illustration. A little bit of time to make sure that you have those. And then I am going to pull the chat out just in case anybody has any questions as you're working, okay? Or to confirm that all your answers. I am looking at the solution in the book in the example problem, and my answers are trending, if you would, right along with the ones that they have.
This might be just me misreading it, but is F1X supposed to be 6 kip, not
Oh,
60
it
kip?
is. It is. Nope, 6. Yep. I think I was gonna put 0.0, but yeah, it's an even 6. Thank you for checking.
Okay.
Appreciate
That
that.
got me nervous for
Yeah,
a
because
second.
I know I must have not written it right because I know on my calculator I looked at it and yeah. Nope. Thank you. Got the same. Excellent. Okay. Now you will notice if we look in the book, what they did is they added, if you would, the negative signs to a couple of these. I encourage you not to do that, okay? And I've told you that before, and the reason for that is we are going to use their directions here to determine their pluses and minuses when we sum our forces, you know, in the appropriate direction. So when we sum our forces in the X to get the resultant X component, or in the Y to get the resultant Y component, then we'll assign that positive or negative at that time, okay? So just absolute values, if you would, for the ones that you see here. I just think that there's the chance for instance, if you have a -6 and then it's going in a negative direction, I don't want you to put it in as a negative and then add the negative, and then by math, it becomes a positive, which indeed it's not, okay? So absolute values here, and then directions come next, actually. So once we have our components, we are going to sum our forces to determine the X and Y components of the resultant, okay? Now, this is where I want to remind you, don't use R for any other random vector when you're doing these problems. Reserve R for only resultants. So that way when we see an Rx and an Ry, and these are capital Rs, then we know that that's a resultant, okay? Don't use that for anything else. I've seen it kind of creep in other places, and that's something that we just want to kind of, by default, you're going to see R, very consistently used, not only in, this class, but in other places as well. So I want to sum my forces in the X and Y directions to determine those X and Y resultant components. So this is important. Everybody follow along here, because I've been seeing on work that's been coming in this looking different and not correct, and I've been taking points off of for it. So make sure that you always let me know what you're going to do. So you have to write, if you would, the equation in variable form before you put any numbers into it. So we are going to sum our forces in the X direction, which is going to equal our resultant X component. We are not working in module 4 here. We're not working problems in equilibrium. When we're in equilibrium, we set that equal to 0. Okay. But in this case, we're going to sum the forces, and that's going to equal our resultant X component, because we're trying to find a resultant in these problems. Okay. So on the left-hand side here, now below, this is where I'm going to go back to my illustration, and I'm going to be looking at horizontal forces and identifying positives and negatives. And whatever I get over here is going to equal my resultant X, okay? Do not, okay, this is what I've been seeing, and I've been taking points off for it. Do not put some of the forces in the X, start listing them out, and then randomly down below add in resultant in the X, okay? No. You've got to tell me what you're going to do before you're going to do it in variable form. So this is going to be the X component of the resultant. So you have to write this first. Have to, okay? It's like you're telling me what you're going to do before you do it, okay? Now what we're going to do is we're going to look back at that illustration, and we're going to fill in, okay, sum the forces in the X direction, and then that's going to be equal to our resultant X component. So I'm going to turn this back over here, and now we're going to look. Forces in the X, that means it's going to be my F1X, my F2X, and my F3X, okay? You'll notice that my F1X is going to the left. That's going to be a negative. My F2X is going to the right. It's going to be positive. My F3X is going to be positive, again, according to my convention, okay? So I am going to go up here, And you don't have to list negative 1x plus 2x plus 3x is equal to rx. That's okay. But what you do need to do is you need to put the value. So I'm going to start with this first one. I'm going to say negative 6 and make sure you write the units in all phases of the problem. Okay, so this is negative 6 kips. Then it's going to be positive 14.14 kips. That's my 2x. And then my 3x, positive again because it's pointing to the right, 24.15 kips. Okay. Now, this is an equation. So we need to set this equal to resultant x. You need to show this step. I want to see the individual forces with their positives and negatives to be sure that you are getting your answer per the convention. Okay. If you just write the sum here and say Rx points off, that's not showing your work. You have to show this step. Okay. I want to see the individual forces with their signs that correspond to our convention. Once you have that, now you can add and subtract here and then say, it's equal to Rx. So if we do this, this is going to be a 6 negative 14 plus, oopsie. Should get 32.29, a positive 32.29. So 32.29, and that's going to be kips are the units, is equal to the Rx component. So I'm going to put my little cloud around here. This is not a final answer, but it's one that I'm going to need and use in, a step that's coming up. So any questions about this and what's required? You have to have sum of the forces in the X equals Rx. And then you have to write out the individual forces with their corresponding positive and negative and units equal to Rx, and then what that sum is. Okay. Now we're going to do the same thing. Thank you, Gabrielle. Now we're going to do the same thing in the Y direction. So we're going to start by sum our forces in the Y equals the Y resultant component. Okay, so you have to tell me you're going to do that. Now I'm going to go back to my illustration. According to my convention, anything going up is going to be positive. So that means we're going to have a positive F1x, a positive F2y, I'm sorry, F1y, a positive F2y, and a negative F3y. Okay, so kind of remember that, and then we're going to write it down below. So now we're going to look at our y's here. We're going to have a positive, positive, minus. So I'm going to write those out. So we're going to have a positive 10.39. Make sure you put your kips behind this. Positive 14.14 and a minus 6.47. Okay, is equal to Ry. So the left-hand side of that equation is summing my forces in the Y direction. The right-hand side is equal to the resultant Y component. So now I can add and subtract these, okay? And it looks like I'm going to get 18.06 kips is equal to Ry. Okay. Oh, hold on. Tim has a question. Does it matter if I write kip? It does not. I do kips and kip, and you'll see it both ways in, yeah, you see it up here too. So kips and kips. I don't know. I should standardize on that. Really doesn't make a difference. Interchangeable. I feel like if it's more than one kip, it should be kips, right? But then up here,
Yeah, it should be.
yeah. But you see it both ways everywhere. Good question. All right, so now I have the two legs of a right triangle to find my resultant, right? So I have a horizontal component and I have a vertical component. Notice our next step here is to draw a diagram of the Rx and the Ry so that we can find the resultant, okay? So you'll notice that both of my values are positive. So that means we're going to be in the first quadrant. So I'm going to draw a Y and an X. Now it looks like, and you can see by the numbers, our X component is 32, our Y component is 18. So along the Y, I'm going to draw my component about that long, okay? And along the X, we'll draw it at least twice, maybe a little bit less. That's going to be my R X. So my Ry is equal to 18.06. We'll do kips. And our X is going to be 32.29 kips. Okay. So labels, you're going to draw them. You're going to show the directions up according to our convention. This is our Y, that's our X axis, and put the units in place. Now that we have the legs, we can then go put a construction line, if you would, parallel to each of the other forces, okay? And our resultant is going to start with its tail at the origin, and its tip is going to be going to the intersection that we just created. We're going to label this capital R, that is our resultant, and then we're going to call this theta, okay? Now we want to calculate the magnitude of our resultant and theta. Yeah, okay. Just wanted to be sure it wasn't calculating that in another spot. So to find R, capital R, we can say that R is equal to the square root of Rx squared plus Ry squared, right? Now we're going to put our values in. So you need to write this. That's the equation in variable form, okay? Always. And now you're going to put your numbers in. So I know that I have 32.29 kips, square that, plus 18.06 kips. And I'm going to square that. See, maybe I got to take my S off. Square that underneath the radical. And the magnitude of my resultant. What is the magnitude of my resultant? 30. Should get 37. Let's get that. That's going to be 37 kips. And this is a final answer. It wants to know what the magnitude of the resultant is, which is one of our final answers. We're not done with this problem, but it's one of our answers. And then just looking for confirmation, everybody's getting that same number. Okay, thank you, Gabrielle. Now we need to identify the direction by finding the angle here, okay? So our angle, if you look here, this is a right triangle that's formed, okay? If we take the tangent of theta, that's going to be the side opposite, which would be equivalent to our Ry. Remember, do not float your Ry out here. Do not float your Rx here. They are located on the X and Y axes. You have to show them and label them here. Okay. You can imagine equivalent lengths on the opposite sides, you know, to see that right triangle, but they are not found out there. So do not add a label or any numbers out here or any vectors. So this is going to be side opposite. So tan theta is going to be equal to our Ry over our Rx, side adjacent. So that's going to be equal to 18.06 kips divided by 32.29 kips. Cancel those two out. 32.29. Okay. So theta then, we should get about 29.2 degrees. That's a box around 2 because this is a final answer. Okay. So now we know our resultant, we know its direction, but we do need to do more work here, okay? If we go back to the original problem statement, okay, we need to locate the resultant with respect to point A, okay? So what we need to find, if I go back to my illustration, okay, here's point A. And I know that, for instance, this is 10 feet here. I know that my resultant is going up in this direction at theta, right? I want to know how far away from A can I place my resultant? And that's going to be what we call X bar. Okay, so it's really just the horizontal distance from our point, and it's going to have the same net effect on the body. So where can I place that resultant so that it's going to have the same net effect as those 3 separate forces? okay? So that's what we're looking for. So that's going to be how we continue on, all right? So if we go back to our process here, we've done the free body diagram, we have the components, we summed our forces to calculate our resultant, so we've got that. Now we're on step number 4, okay? We need to determine the moment generated by the original individual forces about one of the points on the body, and the problem is already stated for us, it needs to be around A. So what we're going to do is we're going to take these individual forces, we're going to rotate them, and we are going to determine the total moment that those separate forces, the components, are creating about point A. So we need to determine that total moment. So that's going to be our next step, okay? So if we turn the page and we go to page 18, that is where we, step number 4 here for this problem, determine the moment about point A, okay? Now, what I am going to do is I am going to remove my paper. You don't have to do that from your handout, but I'm going to remove this so that I can kind of go back and forth and not have to flip so much. So, sum our moment. So we are going to sum our moment about point A, and we need to find what that value is. And I'm actually going to proactively put this all the way over here because I know we've got quite a few forces and I don't even know if I'm going to fit them all on that line. Make it large enough so everybody can see, but you might have to go to the next line. Okay, we're going to sum our moments around point A. So I'm going to go down here. I'm going to put my finger on point A, and I'm going to start up here at point B. There are 2 forces at point B. I've got F1x. Looks like it's going to cause a rotation, okay? We know that a moment is force times distance. So we're going to take the magnitude of this force, and we're going to multiply it by its perpendicular distance away from A. So if we look at the distance away from A, perpendicular to it, 8 feet is going to be the distance, okay? And when we rotate this, this is going in a counterclockwise direction. So according to our convention, that is going to be a positive value, okay? So we are going to start by that first force. We're going to leave a little space here. We're going to start our parentheses. And the first number that we're going to put here is going to be the magnitude of F1x. F1x, the magnitude of F1x is 6 kips, okay? And here's another reason not to put the positives and negatives here, because we don't want to add the direction of the forces in a moment equation. So we're going to say 6 kips times perpendicular distance. We identified 8 feet. I'm only using the symbol here because then it saves a little bit of space. I'll put feet in the final answer. And then we're going to put a positive out front because it is a counterclockwise direction, okay? Counterclockwise. When we are in moment mode, if you would, we are looking at the positives and negatives of rotation. When we are in force mode, some of the forces in the X and the Y, we're looking at which way is it pointing, okay? So that's why we always put this in parentheses, because this is force times distance. This product right here is a moment, okay, causing rotation. Okay, so that's our F1x. Now let's look at F1y. If we pull in the direction of F1y, do you see it does not cause a rotation? If we kind of push it back along its line of action, it would go right through point A. Does not cause a rotation. We're not going to include it. Let's go over to force 2. Let's start with F2y. F2y, yep, causing a rotation. It's going to go counterclockwise, so we'll have a positive out front. Magnitude of F2y. We look back. F2y is 14.14. Perpendicular distance, okay, perpendicular distance. The perpendicular distance of F2y, we're going to pull it back along its line of action down here. It is going to make a perpendicular, so 10 feet is going to be the perpendicular distance, okay? So all of that, we're going to leave a space here, parentheses, 14.14 kips, that's the force, times 10 feet perpendicular distance, and a positive out front because it is rotating counterclockwise, okay? Next force. Put our finger back on A. Go back up here. Let's check the X component at F2. Yep, that's causing rotation. This time we're rotating clockwise. That's going to be a negatively directed moment. The force is going to be F2x. The magnitude of that force is going to come from over here, 14.14. And then the perpendicular distance, okay, perpendicular distance is going to be, if we pull this back along its line of action, so we're in line with A, perpendicular distance here is going to be 8 feet again, okay, 8 feet. So 14.14 kips times 8 feet, negative out front. This one is clockwise. Okay, you don't have to point at the clockwise, counterclockwise if you don't want to. But again, that's the reason for the negative value. This is an instance where we have a positively directed force causing a negatively directed moment. Because remember, this sign out front is based on the direction of rotation to the point that we're summing around, which is point A. Okay, so moment mode is rotation. Sometimes it takes a minute to let that sink in. All right. Let's go back to A and let's look at force 3. Force 3 has X and Y. Let's look at the X component first. Force 3 does not cause rotation. If we pull that back along its line of action, it goes through point A. So there wouldn't be an offset distance. So it would be a 0 moment. So we won't even include it. But the X component does cause rotation. It is going to go counter or clockwise again. So it's going to be a negatively directed moment. Okay. Now, F3Y, magnitude, all right, if we go back over here, magnitude is 6.47. Again, don't put the negatives there because the positive and negatives are going to come from the rotation. Its perpendicular distance, 10 feet, okay? So, going back over here, fix it in 6.47 kips. I'm going to put kips down below times 10 feet. Okay. And then we're going to have a negative out front again, because that's a counterclockwise directed moment. Okay. So as we look back at our illustration, there are no other moments. Don't worry about this resultant. We're going to be placing that. We're just looking at the individual components that are here. Okay. So any questions about what we came up with here so far? Okay. So now we want to multiply and add and subtract, and we want to find that total moment about A. So go ahead and do the math here. So you should get a value of 11.58 kip feet. Remember, we're multiplying kips times feet. So it has to be kip feet, not kips per foot, and not foot kips. All right, kip feet, because it's force times distance. Now I added on here, I said, oh, that's a counterclockwise direction. How do I know that? How do I know that that's counterclockwise? What's my clue? My convention, right? I ended up with a positive value here, right? That's going to equal counterclockwise rotation or counterclockwise direction is the total moment. So the tendency of these forces is to cause this whole body to go counterclockwise. All right. And that's the actual quantity, if you would, of the moment that's going to get us there. All right. So good. Any questions so far? We've got two more steps. The next step, we want to determine the position of X bar, okay? So as we look back over here, remember we drew this little diagram here. We want to find out, we know how much the resultant is. We know its magnitude. We know its direction. It's going up and to the right at that angle theta. But now we want to place it along a line, along A there, so that it has the same net effect on the body. It has the same net effect of 11.58 kip feet, okay, as that moment. So to do that, we are going to use our equation that we had from last time. We know that we can sum our moments around a point, and that's going to be equal to, now, the resultant. I'm going to go like this. I'm going to put a little cloud there. Times, in our case, it's going to be our distance. So it's going to be force times distance. Now, if we look at the resultant, all right, the resultant is acting at an angle, right? It's acting at an angle. So we would have to push this along its line and find the perpendicular distance, but that's not what they want. They want to know how far away from A along that line would we place the resultant. So we're not going to do any of that business, okay? But we already know that there was an RY component and an RX component, right? Which one of those two has a perpendicular distance to point A? Which one of these two components has a perpendicular distance to point
RY.
The RY, that's right, Tim. So look at that. That's our perpendicular distance. So we are going to take X bar times the Y component, not R. We are not going to use that full value. We are going to use the Y component of R. So this is going to be RY. And then the distance is a horizontal distance, and that's why we call it X bar. Okay? So I'm going to get rid of my little cloud here. All right, and it's going to be RY. So if we look here, we know the total moment about A, right? We know the resultant Y component from previous step here, page ahead. We know our resultant Y component was 18.06, right? So the only thing that we don't know here is X bar, and that is what we're trying to find, okay? So now this is an algebraic equation. We can just rearrange this and say, oh, the sum of the moments around A divided by RY is equal to X bar. And now we can fill in our values and solve for X bar. So I'm going to take my 11.58 units in all phases of the problem, kip feet, divided by, say that number was 18.06 kips. Now, notice that both of these values are positive. If each one of these values, if one of them was negative, we would have to put the negative in there, okay? So just be aware of that. These happen to both be positive, so we leave them at positive. Now, we're going to set this equal to R bar, okay? Now, cancel out the units that cancel. Notice that kips cancel top to bottom, and the units that don't cancel are feet. Does it make sense that I am getting units of feet for X bar or a distance? Yes or no?
Yes.
The answer is yes,
Yes.
yes. So the reason, and this is one of those things, the reason that I insist and require you guys to put the units in all phases of the problem, and then, confirm that the type of units that you're left with match the type of variable that you're solving for. If you don't get feet ending up here, then you probably set something up wrong. Okay, so getting the units and making sure that they reconcile to where they're supposed to be gives you a level of confidence that you set up the problem correctly. And that's usually 95% of the problem is setting it up. So now what I'm going to do is I'm just going to go up here. I'm going to do my math, and my X bar is equal to, what's our number? You get 0.641 feet. That's what the book looks like, the answer. Okay. Now, the last step, and the last step for all of your problems, you're drawing me a diagram. Okay. So go ahead and draw your diagram. That's going to include your R, your RX, your RY, theta, and X bar in relationship to A. And I'll show mine down here. So go ahead. You don't have to put all the forces around the outside. We are simply going to draw our rectangle. Okay. We're going to identify point A. Okay. And along that line, we're going to show our resultant. We're going to have that Y component. We're going to have that X component. My proportions are not correct here, but that's okay. So I'm going to have them labeled appropriately. Okay. I'm going to have my RY equals 18.06 kips. My R is equal to 37 kips. My RX is equal to 32.29. Okay. My theta is 29.2 degrees. So again, this lets me know that you understand all the values that you just calculated. Okay. If you're in mechanical design, mechanical engineering, you are usually a very visual person. Okay. So pictures are helpful, right? And then this distance, okay, from A is your X bar. All right. And that is equal to 0.671 feet. And that's the number, I'm sorry, 0.641 feet. 6.4. Now, the double check that you want to do is that the direction of the rotation that is created by what you drew here is consistent with the direction of the total moment that you calculated. So we got the total moment to be in a counterclockwise direction. If I put my finger on A and I rotate this in the direction of, if kind of interfering with my, go down here, interfering with my camera. So I'm in A and I pull in the direction of that RY component, I'm going to rotate, sticking. I'm going to rotate counterclockwise. Okay, you get the picture. Okay. So that is a full problem, 6 full steps. So we started out. Step number 1, free body diagram with our convention. Step number 2, we broke everything into components. Step number 3, summed our forces in the X to get the RX component, summed the forces in the Y to get the RY component. Use those to find the resultant and the direction. Then we had to find the total moment of the individual forces around the point that the problem was asking us to sum around. And we came up with a total moment. Then we set that moment equal to the component of the resultant that would create a perpendicular distance. So this is something that might not always be the Y component. It might be the X at times. So you have to then, determine which one is appropriate. So if this ends up being an X component, then this is going to be a Y bar. Okay. So because then it'll be a vertical distance if we're using the X component. And then rearranging that to solve for X bar, and then drawing a final diagram of your results. Okay, where's that resultant, including its X and Y components, as it relates to point A to have the same net effect on the body that those original three forces had. Okay, it's a good problem. It's a lot of steps. So this is important that when you are submitting your problems for the application problems for Module 4, that you are showing all the steps first and foremost, that you're giving yourself enough room, and that you're not crowding things up. This should be taking you 2 to 3 pages to do. All right. So just kind of plan for that. And then that way you have enough space to show everything that you need to. All right. So that is example 4.6. I'm going to sneak this back in here. Let's turn the page. Let's look at another problem, okay, that is going to use this same process. And this is going to be problem 415, which is on page 74 in your book. So let's go to page 74. Okay, this is actually the problems area, but I didn't want to just give you one example to base your homework on. I wanted to give you at least 2 problems to look at. So I picked one of the problems here from what we have. So down at the bottom, we have a pin connected truss. Okay, we have a pin connecting truss is acted on by the forces as shown. Find the resultant and locate it with respect to points A and D. The illustration is at the top of the following column. So this is the illustration for problem 415. Okay. So here's A, here's D. So we are going to locate our resultant along this line right here. Okay. Now, in this case, we have to take into consideration what's going on, on the truss here. So we will be drawing this out completely. So first step, just like it was last time, we're going to be drawing the free body diagram and the convention. So I'm going to start with the convention because I never want to forget that. I'm going to put that in the upper right-hand corner of my problem. All right. Okay. And now I'm going to draw my truss out. So let me see here. There's 1, 2, 3 sections. Here, I think. Just want to make sure that I get it. Out. I've got A and D on either side here. So here's A and here is D. Got a force coming down at E. It's going to be 15. Oops. And here's point C. And I've got 5 kips. And then we have build a little bit here. This is going to be our last force. This is 10 pips. Okay. And then we are given 3.5 feet. It's going to be our vertical distance here. Each one of these is 3 feet, 3 feet, 3 feet. Okay, which then this is going to be 3 feet. And then these verticals are going to be 3.5. Okay. Now we have one force that is at an angle, and that's that 10 kips up in the upper left-hand corner at what would be point B, right? This is point B right here. Okay. So that means that it's going to have 2 components, right? We're going to have call it BY because it's not giving us a force designation. So we'll call this BY. And then we're going to have BX. Now, the direction of X and Y, this is just a little hint because sometimes when you're doing these early on, you're like, okay, if this force is going, and you can say it out loud, it's going down and to the right. That means that my Y has to go down and my X has to go to the right, okay? So we're gonna show those coming together there. Okay. Now, the angle, you wanna know what this angle is right here, okay? Theta, we'll call it theta. This angle would be exactly the same. Do you see that? Because it's along the same line of action, it would be that same angle. You know what? I'm gonna change the angle here. If you keep it at theta, that's fine. I'm gonna reserve theta for when we do our resultant, okay? So that's typically the one that I do. So let's do this one as alpha. So we're gonna have to figure out what angle alpha is, because then that'll help us for our components down below. So I'm gonna do alpha over here on the left. Now, as we look at the direction of alpha, or where it's located, you're gonna notice that the side opposite is 3.5 and the side adjacent is 3. So we can say that tan alpha is equal to 3.5 feet divided by 3 feet. So these are my units, so those are going to cancel, which makes sense. And calculating for alpha, let me know what you get.
I got 49.39 degrees or 49.4 if you round up.
Yeah, let's go 39 point, I like 39 degrees. I don't mind holding an extra decimal. Okay. So that'll be the angle that we use then to find the components of Bx and By. And that's our very next step. If there wasn't forces that were at an angle here, we wouldn't have to worry about it. So go ahead and do your X and Y component for B. Just confirming. You guys got the same values here for Bx and By. I didn't do them twice, but I'm pretty sure that looks and seems like it's right. Thank you, Connor. Awesome. And Brooke and Gabrielle. Awesome. Thank you. All right. So now we're ready to go to our next step to determine the resultant. Okay. So the resultant, we need to figure out what is the resultant X and the resultant Y component. Then we will determine the resultant itself as well as theta and draw a little diagram. Scooching over. We do have a little bit of room at the top here. So I just wanted to make sure, because I'm like, that's not very much. So we are first going to sum our forces in the X direction to find the resultant X component. So we want to write that out. Remember, you have to tell me what you're going to do first in variable form, and then you're going to do it. Okay. So sum of the forces in the X is going to equal the Rx component, the resultant X component. So we'll go back up here and we're going to look, okay, what forces do we have in the X direction? So we've got a positive Bx, which we know to be 6.509 kips. And we have a positive 5 kips. Again, both positive because they're going to the right. So I'm going to say, okay, a positive 6.509 kips plus 5 kips. Okay, that is my sum of the forces in the X side. Equal to Rx. This is an equation. It has an equal sign. It has two sides. So make sure that you write that. Do not just go right to adding those two together. I want to see the values with their respective positive or negative values according to the convention. If you just write a number here and it's not right, I don't know what you did wrong. Okay, so you have to write those out. And then add those two together. Okay, so this is going to be, looks like it's going to be 11.509 pips is equal to Rx. Okay, so we'll just kind of put this on the side here. Now we're going to do the same thing in the Y direction. We're going to sum our forces in the Y direction equal to the resultant Y component. So we're going to go back up. We're going to look. What forces do we have in the Y? We have a negatively directed pointing down BY. We know that it is 7.592. And we have a negatively directed pointing down 15 kips. So we're going to do a negative 7.592 kips minus 15 kips is equal to RY. Again, it's an equation. We need two sides, right? If we're saying we have two sides here, we have to have two sides here. So make sure you set that equal to RY. So if we have 7.592 and 15, we're going to have a negative 22.592 pips equal to RY. And the negative just means that it is pointing down. It gives us the direction. The positive here says that this one in the X direction is going to the right. All right. Any questions on those? Everybody get the same number I did? So pretty straightforward. Okay. So now we're ready to turn the page. Actually going to tear it off because I think it's going to be easier to work with. And now at the top here, we're going to determine our resultant and its angle, okay? So now in the case of our Y, it was going down, right? We had a negative value. So that means we're going to be working, and our X was positive, we're going to be working in the fourth quadrant, okay? So from the previous page, we know that our X component was 11.509 and that our Y component was 22.592. So we have a Y that's going to be longer by about 2 times as long than our X. So this is our RY equal to 22.09, right? No, not at all. 22.592. And that's kips, okay? And it's going down. And then about half that distance, proportional, you don't have to scale it, is going to be our Rx. Rx is equal to 11.509. And that's kips. Make sure you put the units, okay? This is our X, and this is negative Y. Now, the resultant. Simply going to kind of draw some construction lines here where they come together. Starting at the origin, the tail of the resultant is going to start there. Its tip is going to go to the intersection we just created. Okay. And then the angle is going to be theta. So now over here, we got to find the magnitude of that resultant and the magnitude of theta. We know that this is a right triangle. R is going to be Rx squared plus Ry squared. Okay. So our resultant is going to be equal to 11.509 pips squared plus 22.592 pips squared, all under the radical. So my resultant is going to be 25.355 kips. Confirm that number. I just did it one time.
I got it.
You got it. Thank you. Awesome. Now, the next thing is we want to calculate theta. We know that it's going down and to the right, and we know its magnitude, but we need to know the angle that it's at, right? So we've got theta labeled here. So now I'm going to say, all right, tan theta. I always use tan because I'm going to use the X and Y components. They are, if you would, the least or less calculated than what the resultant is. So I'm going to go side opposite, which is going to be our RY over our RX. And we are going to have the 22.592 kips over the 11.509 kips. Those cancel out, which makes sense. And our theta should be 63 degrees. Just looking for a confirmation on that too, as you guys are coming up with your answer.
Yeah, I got that.
Awesome. Okay, thank you. All right, so now we have our resultant. We have its direction. Okay, so that's a big part of the problem. But now we need to locate it. Okay, now we need to locate it. So if we go back to our original illustration and the problem statement, okay, the problem statement, which is at the bottom of page 74, we want to find the resultant, which we just did. Okay, we've got the magnitude, we've got its direction. Now we want to locate it with respect to points A and D. So all that means is we want to put it along this line, and we could pick either A or D to sum our moments around, but just to kind of go with, what we do, I'm going to go on the left-hand side, and we're going to sum our moments around A, and then our distance is going to be an X bar distance again, okay? And it's going to be, a distance from A. So, let's see here. I want to go back to our procedure. We already did our free body diagram convention. We broke into components. We just did our resultant. We are at that step number 4 again, determine the moment generated by the original individual forces about one of the points on the body, which is going to be point A. So that's what we need to do. We're going to put our finger at A, and now we're going to sum our moments in the directions of any forces that are causing rotation. Okay? So it says you get to choose, but I'm gonna do A. So I'm gonna kind of start over here again so that I have enough room. I'm gonna sum my moments around A equal to, it's not equal to 0. Okay, we want to find what the moment is that's generated based on those individual forces. We want to get an actual value of a moment. Okay, so starting at A here, I'm gonna go up to B. I'm going to rotate in the direction of the BX component. Causes a rotation, it's going to be clockwise, so we know that that moment is going to be negative, right? The magnitude of BX, 6.509, perpendicular distance. If we kind of back it up along this distance here, this is going to be that perpendicular distance. That is going to be 3.5, okay? So if we go on the next side here, 6.509. I'm going to put kips down below because I want to make sure I fit in here. And this is going to be 3.5 feet. And then it is going to be rotating clockwise. So again, that negative out front is clockwise. There is no other way to write this except to put your moments in parentheses. The book doesn't do that. And I am insisting that you do that. You will get points off if you don't show your moment in the parentheses. And the reason for that is this sign out front is for the rotation of the moment, the product of force times distance. If you leave the parentheses off, it makes it look like the 6.5 is negative and not 6.5 times 3.5. Okay. So it's really important that you put that on. All right. So that's our first one. Put our finger back on A. And now we're going to pull in the direction of the y component. It causes rotation as well. So we're going to take the by, magnitude is 7.592, times its perpendicular distance. We're going to push it along its line of action. Its perpendicular distance is going to be 3 feet. And then the direction of rotation is going to be clockwise again. So that's going to be negative out front. So 7.592 times 3, negative out front. Okay. Clockwise again. Next one. Put our finger on A. Let's look at that 5 kips. Yep, that's causing rotation. So the magnitude is going to be 5. Back it up along its line of action. It's going to have that same distance, 3.5. So 5 times 3.5 is the moment, the magnitude of the moment. And it is going clockwise. So it is going to be negative out front. Here again, 5 kips times 3.5. And negative out front again. Okay. One more. And finger on A. Pull in the direction of the 15 kips. Yep, causing rotation. Perpendicular distance here, a total of 6 feet. So 15 times 6, causing a clockwise rotation. Here we go. And those are all of the offset forces causing a rotation. So now you're going to get your value of your moment. Okay, so go ahead and multiply those out and add and subtract. I'll do it here too. One more time. Same number. Okay. So just want to confirm, I did do it twice. I ended up with the same value. That's what you got. Awesome. Thank you. Thank you. Thank you. All right. Now, this is the total moment. This is the total moment. So if I go back to my procedure, last step. Too many pieces of paper. Here it is. Okay. We determine the moment generated by those individual forces. Now what we want to do is we want to find the X bar or the Y bar. Now, it will be an X bar again because we go back to our illustration here. We are going to be along this line. So we're going to locate it along there. Okay, it's going to be a horizontal distance. Okay, so we are going to do an X bar. So we know that sum of the moments around A is going to be equal to our resultant. Now I'm going to put this little cloud around here again. We're going to fill that in and we are going to be doing an X bar. Now, if you kind of remember from last time, we did an X bar, right? We had an X bar and we multiplied it by the Y component. Let's see if that's going to work again. So what I'm going to do is I'm going to kind of go ahead here and I'm going to draw my line, okay, from A to D. So here's D, here's A. And this is that line between those two. And I want to locate my resultant, okay? So here's my resultant. So somewhere along there, and I don't know exactly where it's going to be, but I'm going to have my RY. I'm going to have my RX, and I want to show this diagram, okay? And then I'm just gonna put the instruction lines here. And this is gonna be my resultant. And I know what theta is, right? So if I look here, I know that my R bar or my X bar is going to be going along here. As I look at my resultant, is it going to be the X or the Y component that is going to give me a perpendicular distance? Am I going to use the X or the Y component to find X bar?
Y.
The Y component again, absolutely. So I'm going to get rid of this guy. Okay, and remember, if we are doing a vertical distance, a Y distance, then my resultant component is going to be the X component. Okay. All right, so I know the magnitude of my RY, and I'll fill in those numbers in just a bit. I know that from up here, 22.592. I know my total moment around A because I just calculated it. So we're just going to rearrange this to be some of the moments around A divided by RY is equal to X bar. Okay. And then now we can fill in our numbers. So I'll do that. I'm going to say equal to here, and I'm going to put it alongside. So I know this to be negative 153.06 kip feet. Okay, put the units in. Negative, because this was negative, it came out negative, and we know that that also means that we are going to have a net rotation that is going to be clockwise in a negative direction. Now I'm going to put my Y component down below. My Y component is a negatively directed 22.592 kips. Okay. Kips cancel. Negatives become positive. Okay. My X bar is going to be, this is a positive up front, divided by 22.592. So 6.775 feet. That is one of your final answers, right? Where to locate it. Now, we go down here, that means to the right of A, positive value, this is going to be equal to 6.775 feet. I'm going to put in my X values here, 11.0, 11.509 kips. My RY is going to be 22.592 kips. My R, 25.355 kips. And my theta is 63 degrees. So again, putting all of these elements in place so that I know that you know what the answers are that you just calculated. Okay. Questions. So we did the same process, okay? We did the same process. We started out with our free body diagram. We calculated our components, summed our forces in the X and Y to get our resultant X and Y components. We use those components to determine the magnitude and direction of our resultant. Then we determined the total moment that the individual forces created so that we could then determine where are we going to locate that resultant so that it has the same net effect on the body. That's what this equation does for us. Solving for X bar and then drawing our final diagram. Okay. So now this leads us into the, you have the ability to do the homework that's assigned. Okay. So, so the next problems that you have assigned are going to be 1412. I'm sorry, 412 and 416. Okay. So the first one here, we have a cantilever truss. That just means that it's supported on one end and then it's free, out on the other end, kind of like a diving board. It's acted on by the forces as shown. Find the resultant and locate the resultant with respect to AC. So this is really where you're focusing, okay? So you've got a line from A to C. You've got three forces. One is at an angle, okay? So you'll have to resolve that into its X and Y components. And you want to find where is the resultant that's going to have the same net effect on the body as these individual forces. And where am I going to locate it along that line? Since this is a horizontal line, this is going to be an X bar. So you're going to have your moments around A, okay? It's going to be equal to your RY component, just like we've been seeing in the last two problems, times the X bar, okay? And that X bar value is going to give you your distance from A. That resultant is going to have the same net effect. Go through that same process and make sure that you include all of the elements that we did in the last two problems, including a final diagram. Okay. That's your first problem. Your second problem is going to be 416. Okay. 416, we want to determine the resultant of the forces acting on the pin-connected tower as shown. Locate the resultant with respect to the right side of the tower, FJ. So this is the right side right here. It's a vertical line this time. So you are going to sum your moments around, or not around A, you're going to do it around J because it wants it in respect to this line right here. Sum the moments around J. You're going to use your RX component and it's going to be multiplied by a Y bar. So your Y bar is going to be locating that resultant. Okay. All right. So that's kind of our next big section. Okay. If we look at our handout or our guided notes, that brings us through page 20. Okay. And our next section here, and it's a very small section. It's the last section in this chapter. So on page 21, we've just got a little bit left. Okay. Very little bit left. And that's going to be the last two problems. So we have, if we look at our application problems, you're going to notice that you now have the ability to do all of the problems through 16. And then we have two problems left. And I'm going to save those two problems for the next time we get together. It's going to take us all of about probably a half hour to do these. Okay, do the example or the examples and kind of go over it. So it's a short little section, then you'll be able to finish up those last two problems. Okay. So what I'm going to do right now is I am going to stop the recording